that has a positive cell potential. Turns out that this cell potential, standard, is 1.1 volts. As the electrons go from the zinc to the copper, it's going to give us a voltage of 1.1 volts. The zinc would be the anode, since electrons are leaving it. Copper is the cathode, since electrons are going to it. But you have to know for a galvanic cell, this reaction must be a spontaneous reaction. No. You've drawn enough galvanic cells. You might have to. I would just want to show you a contrast between that and the electrolytic. Okay, now here is what an electrolytic cell looks like and does. We didn't need any help for this reaction to happen. We just set it up and the electrons flow. Doesn't need anything from us. However, what if we want the electrons to go the other way? And there are cases where it'll be important for us to have the electrons go the other way. Maybe we need a reaction that will make zinc metal. This reaction, the way it's written, is reducing the amount of zinc metal. So it may be a case where we have to make some zinc. So we'd have to force the electrons the other way. In an electrolytic cell, you're going to need some help. We're going to have to force the electrons to go in the non-spontaneous direction. That's what an electrolytic cell does. We're going to have to take advantage of an external current, like something that we plug into the wall, that's going to force the electrons back in the opposite, non-spontaneous direction. So I'm going to show you part of this drawing. Part of this drawing you're going to see, there's some letters here that I don't want you to see yet. So this is the same setup. I got the zinc on the left and the copper on the right down here, although you can't see it. But the big difference between the two pictures is this thing right here. The electrolytic cell, if we want the electrons to go the other way, the non-spontaneous way, we need a power source. We need something that we can plug in. It's going to force the electrons. Now, right back there behind Rishi is a ugly blue box. It's actually even crooked. It doesn't have all of its feet on it. It's old. That is a power supply. Right now it's not on, so nothing is happening. But when I turn it on and crank up the voltage on it, it's going to move the electrons. And I'll show you that because we're going to use that today. But notice the flow of electrons. They were going from left to right when it was spontaneous. The power supply is going to be taking the electrons and moving them from right to left. Now, as long as we want this thing to happen, the voltage that we cause the power supply to give us has to be greater than 1.1. If I only use like 1 volt, the spontaneous side would still win. It would still go to the right. But I need to use greater than 1.1 volts, and then that would force the electrons to go the other way. And now, the thing I was covering up was this. Now, let's see, I'll move this up a little bit. Since the electrons are going the other way, that makes this side the anode. This side that was originally the cathode receiving electrons, now the power supply is causing us to give up electrons. So the copper metal, which was building up the copper metal because things were reducing on there, now is starting to oxidize. And the zinc, which was shriveling up because it was losing all of its zinc metal atoms, is now going to get built up. That would be the cathode. All this happens because of the power source. It's always a non-spontaneous reaction, so we have to make it happen. So electrolysis is going to be handy for making things that would not be found in nature. The best example I can think of right off the top of my head is sodium metal. Sodium metal is an extremely reactive metal. You'll never find sodium metal in nature because as soon as it rains or as soon as it touches something else, the sodium reacts. So there's lots of sodium ions out there, but there's no sodium metal in nature. It'll just react with pretty much anything. So how can we get sodium metal? We actually have sodium metal in our department here, and it had to be produced from sodium ions. And the process for which, or by which we make sodium metal is with electrolysis. All right, are we good with this slide? Then go on to the next one. This example is going to show us how we could make sodium. The chemical equation that we see here represents a spontaneous reaction. When you have sodium, the metal, which is very reactive, and chlorine, the non-metal, which is very reactive, put those together, and that's a no-brainer. They're going to react, and it's going to make sodium chloride. This being a spontaneous reaction means that sodium chloride is more stable than sodium and chlorine were by themselves. This is made, a whole lot of energy is given off. Actually, it does decrease in entropy, which is not favorable, but there's a huge release of enthalpy, delta H, big time negative. Like this thing will explode, it'll make sounds and really bright light given off and hot. So yeah, a lot of energy given off. So in the forward direction is spontaneous. Could we get the reaction to reverse? What would we have to do to have it go in the other direction? You can't just tell the reaction, now go in reverse, and expect it to listen to you. It's not going to. We have to force it to do that. Because naturally it's going to want to make more sodium chloride until one of the reactants is gone, and then stop. So in order to reverse the process here, what type of reaction is this? You remember from your types of reaction in Chem 1? The synthesis, decomposition, single replacement, double replacement, combustion. This is a synthesis reaction, yeah. There's two things reacting, one thing is made, synthesis reaction. It's also a redox reaction. Because the sodium starts as neutral and it becomes positive 1, yeah? And the chlorine starts as neutral and becomes negative 1. So it's a redox reaction, transfer of electrons. Any redox reaction we can force the other way with a power source. So to get the reverse reaction to occur, here's what we're going to do. I'm going to show you a picture of it. Now, for right now, don't write anything about the anode and the cathode. I want to describe this first. So what you would do is, in this case, this is different from what we saw in the previous slide. The previous slide showed two beakers like the opposite of a galvanic cell. This one, in most electrolysis setups, you just put one substance into one beaker and take two electrodes and put them both in there. Now the power supply, again, like that blue thing back there, that's a power supply. That, you plug it in and you turn it on, you crank up the voltage, and this is going to force something to get oxidized and something to reduce. Now, I see there's a number of you that are writing down. I'm going to be quiet for a second because I want you to hear the explanation on this. Right fast. I want to actually show you a demonstration. In fact, I'm going to go ahead and turn this thing on back here because it needs to run for a while. This is what happens with electrolysis. Now there's several things that I want you to notice here. The first, I guess, I'm going to get this out of the way. This will not work if sodium chloride is a solid. And that's a royal pain right off the bat, because if we want to electrolyze sodium chloride, we got to heat it up super hot to get it to melt. Molten salt. In fact, the title says it only works for molten salts. The reason is because for the same reason we needed a salt bridge in a galvanic cell, you need the circuit to have charge flowing all the way through it, which means even between these two there has to be charge flowing. Same kind of thing with a salt bridge. So that power supply is hooked up. There is a wire going out of the power supply into one electrode. It's probably a platinum electrode. And the other side has a wire going from the terminal to a platinum electrode. And you just crank the voltage. Now, cranking the voltage means this. The power supply is going to move the electrons from this electrode to that electrode. Which means if that is non-reactive, like platinum, and that's non-reactive, like platinum, that means something that the electrode is in must oxidize. Something has to give up electrons in order for the power supply. The power supply is like a bully. It's forcing electrons up into it and then it's giving the electrons back out there. And so that means that it's going to take electrons from somebody in here, even if they don't want to give off electrons. They're not interested at all. Now you have a choice. Sodium is positive 1, chloride is negative 1. These already have made their ions. One of these two things, because that's all that's in this thing, one of these two has to give electrons up for the electrons to go up into the electrode and through the wire. Which one can give up electrons and oxidize? Can the sodium positive 1 ion oxidize? Does it have any electrons it can give off? Now I want you to consider this. Look at sodium on the periodic table. Sodium is number 11. It loses 1 electron and makes positive 1. At that point, it has a noble gas electron configuration. That's what it is right here. Do you think sodium is interested in giving off any more electrons? No, it won't. It can't. It doesn't. It won't do it. Because it has a noble gas configuration, it is ultra stable, it's not doing anything. Now chlorine, on the other hand, is the chloride ion. The chloride ion has gained 1 electron, and it's a negative 1. Is it possible for chloride ion to give up its 1 electron that it gained? The answer is yes. Even though the chloride ion was ultra stable at negative 1, something has to give off an electron, so the chlorine ion is it. It's just stuck doing it. It had gained 1 to get to this condition, it's going to have to get rid of it. Whereas sodium, we've never heard of sodium making a positive 2 ion. It doesn't ever lose 2 electrons, it only loses 1. It has lost that 1, then it's done. So, yeah, that's why I have labeled here the anode, which is right here. Remember, that's where the electrons are coming from, is the anode. That's chloride ion by force giving up its electrons. It doesn't like it. The electrons are shoved through the power source and into the cathode they come. Something has to reduce at the cathode. The chloride ion cannot reduce. Chlorine has already gained the 1 electron to make it negative 1, and they're already migrating toward the anode anyway. So the sodium ion is stuck accepting the electron. The chloride ion cannot accept an electron. It has gained 1 to make it negative 1. It's not gaining any more. We've never heard of chloride negative 2. Have you? No. So the sodium is stuck accepting the electron. So what we would observe if we saw this thing happening, if we saw this cranked up, I can't show you sodium chloride in an electrolysis setup because I have no means for melting sodium chloride. You got to have this like at 600, 700 degrees. We can't do that. So anyway, what we would see though is chlorine gas being made. See at the anode right there, we're making chlorine gas. So you would see yellow cloud. That's like the Bellino effect, right? We told you about that. See this yellow cloud coming up from that electrode. And over here, as the electrons come in, there would be sodium, a soft silver-colored metal coating this. That's how sodium metal is obtained. Factories do this on a large industrial scale, those that would want to make sodium for whatever reason. I'm glad that some do so that we can use some of the sodium here at school. But yeah, that's how sodium is made, is it will be just electrolyzed and coated on that, and then they'll just scrape it off and store it. So you get sodium and you get chloride.